Welcome to this video on statistical mechanics, which I've made for my students in statistical mechanics at the Delft University of Technology. My name is Jos Thijssen. This video deals with, in fact, what particles do in a liquid or in a gas. They follow an erratic motion, which is of course very difficult to describe. And it's also not particularly interesting what a particular particle does. But on the other hand, the statistical properties of the motion of particles is of quite some interest. A phenomenon like diffusion can be described in this way if you know the average behavior of the particles. And in order to get a handle on this behavior, we make some assumptions concerning the forces that act on these particles, and they are due to the surroundings of the particles. We don't want to have a detailed theory for the cause of these forces and then derive the form of the force from it, but we make some assumptions about the force which are reasonable, at least in some limits, and from that we infer what the properties, the average properties of the motion are. And in the end we will be able in this way to describe diffusion, also drift and diffusion. And it's important to realize that the techniques that we use are not limited to particles moving in a liquid or in a dense gas. They are widely used, in fact, for degrees of freedom that are subject to fluctuations of which we don't have too detailed information. And therefore we always make the very similar assumptions to the one that I make in this movie. I hope it is useful for people watching it. Here you see a molecular dynamics simulation of a Lennard-Jones gas. Those are atoms which interact via a Lennard-Jones potential, attractive well and a repulsive core. And the particles are atoms. They are rendered by blue dots, but there is one particle which has been singled out. That's this blue particle here. And the blue particle is just one of the atoms. It's an arbitrary atom, and by giving it a different color, it's easy to see how it moves through the gas. And as you can see, it's a kind of random walk motion. The particle receives kicks from the other particles, and that moves the particle, the blue particle, around. And we shall see that although the motion for each individual particle is completely impossible to predict, it's possible to make definite statements about the motion in general that the particle makes. So we can make statistical statements about that motion. And that is the subject of this movie. In fact, we focus on the special case where we have a large particle, that's this disk here, which is moving in a dense gas or fluid consisting of small particles, and they bounce off this large particle, and that gives rise to the famous Brownian motion. And its motion is determined by the light particles which collide many times with the heavy ones. So the disk is moving slowly and the other particles are moving a lot faster, because equipartition tells us that the kinetic energy is equally distributed over the particles, but a heavy particle then has a much smaller speed. The effect of the collisions by the light particles with the heavy particle is twofold. First of all, the heavy particle will feel a drag. You can imagine that if the heavy particle moves at some speed through the liquid, it will experience many more head-on collisions. Then it will experience kicks in the back. And therefore its speed will slow down until it comes approximately to a rest. So the first force that the heavy particle feels is a drag force. On top of the drag, it will feel random kicks in all possible directions, and so you have random kicks on top of a drag. So first of all, you have the drag, and then there are random kicks that even if the particle has come to a rest, there is no drag anymore, but there will be random kicks in all kinds of directions. We want to capture the effect of both the drag and the random kicks in an equation of motion. The drag force is easy to incorporate because we know its form. It's minus gamma times v. That's the usual form for the drag force. Then the random kicks, we represent them just by a force r, which is a vector, and it must have some random character, and that represents the random kicks. And eventually there is a field like gravity, or if the particles are charged, it may be an electric field, which is a systematic force. And we can include that, and we call it F, depending on position and time. So the F is a systematic force. The drag force and the systematic force are rather familiar, but the same cannot be said of the random force. However, although the random force itself is by nature unpredictable, we can make some statistical statements about it. So we can make some statements about the statistics of the random force. The first property of the random force is that its expectation value is equal to 0. For all times. So imagine the fluid or the gas being at rest, which means that its center of motion is at rest. Then obviously if I put a particle in, and I put a particle initially at rest, it will get random kicks from all directions, and these will average out. That's an average in time. So what does the average here with the angular brackets mean? Because this is evaluated at one particular time t. Well, the average expressed by these angular brackets is an average over all the possible realizations of the random force. So if we start a simulation or an experiment, we get a certain random force, then we do it again and again and again. So we have a long series of random forces at subsequent times. And if we average over that series, then it turns out that this random force is 0. So the angular brackets represents an average over all the possible realizations of the random force. The second property of the random force is formulated as a statement about the correlations. So imagine we take the random force at some time t, at some arbitrary time, and then we take the random force at some time tau later than t, so t plus tau. In that case, the expectation value averages out to 0 whenever the tau is greater than 0. So when we look really at a later time, the random kicks have nothing to do with the random kicks that you saw before. Now in a liquid we know that is not true, because in a liquid you have hydrodynamic correlations. So this is an approximation, and in fact that approximation is valid for heavy particles, because they will experience many collisions before they change their position appreciably. So if the time scale at which the heavy particle moves is a lot slower than the correlation time in the fluid, this is a good approximation. However, if I take just one atom feeling random kicks by the other atoms, it turns out that this assumption is not valid. So why do we make that assumption? It's for mathematical convenience, because it enables us to infer all kinds of properties without too much mathematical effort. This is therefore an approximation that is made very frequently. So it says that the correlations between subsequent random forces vary. Of course, if tau is 0, then I just have the expectation value of the random force squared. The final property of the random force is that it's subject to a Gaussian distribution. So each force is drawn from a Gaussian probability distribution. PR represents the probability density for finding a random force of size r. This should in fact be a vector, but you can read this as one component of r. So each component of r is subject to this probability distribution, which means that if we run, for example, a computer simulation, we draw a random force at each time from a Gaussian random distribution, and then we feed that into the equation of motion. And we do that for each component, so that's why R here is not a vector but just a number. When discussing random forces, it's anyhow convenient to think in terms of a computer program, and in a computer program what we do in order to solve the equation of motion is to discretize the time. So we have time steps t1, t2, etc. They are equidistant, which means that the distance in time between two subsequent time steps is always delta t. In the simulation we generate a random force for each time step, and the properties that we have formulated before translate into the following recipe. The probability density for having a random force R1 at time t1, R2 at time t2, etc. is given by this expression, which is a Gaussian expression, and the fact that the forces are uncorrelated at subsequent time steps just causes this probability to be the product of the individual Gaussian probabilities. We can then return to the continuum notation. We have a sum over r's at subsequent time steps. We can formulate that as an integral if we divide by an extra factor of delta t. And so we have now formulated the probability distribution as a continuum distribution, and we use a shorthand notation 2q for the denominator here, and so this is our continuum prescription for the probability density of having a force between t1 and tn. If we then recall our prescription, which was that the correlation function of the random force led to a delta function, we can write for Rn, Rm, and this is now one-dimensional, that it's equal to r squared delta m and m. That's now a discrete delta function in the discrete time. It is interesting also to consider the correlation property of the random force. We can formulate that also in discrete time. Note that I have taken here a scalar r, so this is one component of a vector random force. And in discrete time, this will give me an Rn times Rm, random force at times Tn and Tm. And that is equal to the average value squared times, well, this delta function in discrete time turns into a delta Nm divided by delta t. Because the integral over the delta function is 1, we need the 1 over delta t here. And due to this property here, we see that the width of r squared is always this q. So we have a q over delta t times delta nm. So this r squared is just q based on the properties of Gaussian integrals and the second moment. Next we turn to the solution to the Langevin equation, and in general that solution is difficult to find, but in the case where the systematic force is equal to 0, we can make some statements about the solution. So that's the case where we will be now, and the Langevin equation then reads as follows. We have mv dot is minus gamma v, that's the drag force, plus r, which depends on t, and which is a random force. This equation is called the Langevin equation. The Langevin equation is a differential equation in V, and it's a homogeneous equation for one dimension, and therefore we can first try to solve the homogeneous solution. So we take r equal to 0, and then we are left with this equation, and that gives us the homogeneous solution. V wiggle is v wiggle 0 times e to the power minus gamma t over m. So this is the homogeneous solution. Then we need to find a particular solution, and we do that using the standard method. We try a solution of the form Vt is the homogeneous solution times some function that depends on time. And if we plug that into the differential equation, we get the following. First of all, we have two time dependencies, one here and one there. So we get two terms from the m times v dot. Those are those two terms, and on the right hand side we have here the drag force, and here we have the random force, and the drag force is cancelled on the left and right hand side. So here you see that this term is identical to that term, and so we are left with a simple equation for f. This equation can be directly written as f dot is some function on the right hand side which depends on t, and this can easily be solved. When I say solved, it means writing the solution formally as an integral over a function involving the random force, and because we don't know the random force, there is no way we can integrate this function analytically. Putting this f into the form for v that we have written here, we obtain the following solution. We have here the particular solution, that is the one we just found, and this is the homogeneous solution, which we can add with an arbitrary prefactor. And because we take the integral from 0, this prefactor should be the velocity at time t is 0. As mentioned before, the second term is not amenable to analytic solution, but we can definitely infer some statistical properties of the solution for v using the statistical properties for r. We can, for example, calculate the expectation value of this v. We put angular brackets, which means that we average over all the possible realizations of the random force, and because the average value of this random force equals 0 for all times, the solution will just be the first part because the second part vanishes. So on average we can find what the v in the course of time is. Obviously that's the average behavior, and it's interesting to see how v would vary around this average solution. In order to find that out, we calculate the v squared of t, so that we can later subtract the v expectation value squared. That's this expression, so the difference is this term. And now we have here two r's, because we have two integrals. We have first an integral for the first v, and then for the second one we call the integrand the integration variables t1 and t2. And therefore we have an expectation value of rt1 and rt2, and we know from the statistical properties of r that we can write this as q times delta t1 minus t2, and that simplifies the integral a lot. Working out the integral, we obtain the following result. So here we have a q which now enters in front of a single integral because we had a delta function. The delta function tells us that t1 is equal to t2, so we have now 2 times gamma, and I now have called the integration variable t primed. We can carry out this integral. It's a very simple integral, and the result is that we have v0 squared times minus 2 gamma t over m plus q over 2 gamma m times 1 minus e to the power of minus 2 gamma t over m. So what do we have? We have an average behavior, and that average behavior is typically the solution to a drag equation, exponentially damped velocity, and we have also an expression for the variation. So if we subtract this term from the left and right hand side, this turns out to be the fluctuation, the average value of v with respect to its average velocity. And we see that for long times this term decays, and we are left with just q over 2 gamma m. So for long times the first term of course decays to 0, also this term decays to 0, and we are left with a constant for the expectation value of v squared. So here I've written down that very same statement. It's q divided by 2 gamma m, that's the expectation value of v squared. But if the particle is in equilibrium in a liquid or in a gas, we know from the equipartition theorem that the velocity squared expectation value should be kBt over 2 over m. And therefore we find an expression for Q in terms of the temperature and the friction coefficient. So Q is 2 gamma kBt. So what we have achieved is the following. We started with a random force acting on particles, and that of course renders any solution impossible. But what we have found is that the statistical properties of the particles are known. So the expectation value of the velocity, for example, we know that that is decaying exponentially, and the fluctuations will decay to a constant. And using the equipartition theorem, we can relate that constant to the width of the random force, Q. So the width of the random force together with the drag determine the final kinetic energy, so the final temperature of a particle in the fluid. Although we have motivated the Langevin equation from the context of a Brownian particle, it should be emphasized that the analysis is representative for stochastic processes in general. So if you have a system which is out of equilibrium but which relaxes towards equilibrium, it can be described generally by a Langevin equation where the minus gamma v is responsible for the tendency for the system to go towards equilibrium, and RT represents the thermal fluctuations. And what we want to do now, it's a very common approach, is to derive an equation for the probability density for v. So for the variable which is varying in time, which is relaxing towards equilibrium under the influence of thermal motion. Well, if we look at the Langevin equation, what it tells us is how the v at some time t plus delta t is related to vt. So it enables us to go from a velocity at time t to a velocity at time t plus delta t. And therefore it's natural to also find find an equation. Looking again at the Langevin equation and realizing that it allows us, when we discretize it, to go from a velocity v at time t to a velocity v at time t plus delta t, it seems natural to also try to find this p as from an evolution equation which relates p at time t to p at time t plus delta t. First of all, in order to facilitate the analysis, we take the mass equal to 1, so we drop it from the equation. And then this equation, if we discretize it, tells us that if we start with a velocity v primed, we will go to a velocity v at the next time step, which is related to v primed by this equation. And the probability that we go from v to v primed is the probability with which we can generate a force, a random force r, which satisfies this equation. So the probability to go from a particular v primed to a new value v is in fact the probability of this r. So we start from a probability distribution at time t for all possible values of v primed, and we calculate the probability for ending up with p of a velocity v at a later time. And then we have to make a transition, and the transition is made by this random force. So we integrate over all the possible values of the random force. So this integral is going from minus infinity to plus infinity. And the curly p here is the probability density for r, and we know that that's a Gaussian probability density. So this is a Gaussian probability density, and it relates via this integral the p at time t to p at some later time. Now we know the following. If the time delta t, if the time difference is small, then it's very likely that this v is very close to v primed, because the random force can be large, but that it has a rather low probability because of this probability density curly p being Gaussian. And because of the delta t, in general, the v primed and the v will be very close to each other. So this v primed is close to v, and therefore it is obvious that Taylor expansion is the way to go now. Here I've Taylor expanded p in the integral as a function of v primed around the value v primed is v. The first term gives me an integral of p of v, because that's a zeroth order Taylor expansion. Then I have the curly p of r, and then I have dr. I can extract this pvt in front of the integral because it does not depend on r. You see, only v prime depends on r, but the v is given. And then the integral over prr, well, that should be a normalized probability density. So I simply get p as a function of v and t. Now the remaining two terms are the first and the second order Taylor expansion of v primed around the value v. Now from the evolution equation here I can immediately infer that v prime minus v is given as a gamma v minus r. So I've plugged that in here. Now the derivative here is taken at v, so that does not depend on r. And if I take the integral of r over the Gaussian probability distribution, due to the anti-symmetry, this integral gives me 0. So that's in fact an expression of the result that the expectation value of r over all the possible realizations of the random force gives me 0. So I'm left only with this term from the first order Taylor expansion, and then I still have this second order term. Then we subtract on left and right hand side pvt, so that on the left hand side we have a finite difference for p at t plus delta t and t, and I can write that to first order in delta t as delta t times the partial derivative of p with respect to time. Then on the right hand side I first have this term with the gamma v. This term is independent of r, and if I take the integral of over the curly p of r times dr, that's a normalized probability distribution, so it gives me a 1, and this is the result of that term. And the remaining terms are treated very similarly. So here I have a half times first gamma squared v squared times delta t squared. This term is independent of r, so I can also put it in front of the integral, and then I only have the integral of pr dr, which gives me a 1. Then I have a term which is linear in r, and I multiply that by pr dr, so that's the expectation value of r itself, and that vanishes. And then the last term is the term where I have an r squared. But I know what r squared is because that's the width of the Gaussian. We have seen before that was 2 times gamma times kbt. And therefore the result is this line here. Now you may argue that I've not been consistent, because here I have taken only the first order term, whereas here the terms contain also powers of delta t squared. So why did I omit those terms here? Well, in fact I'm working to order delta t on the left and on the right hand side, but it's important that this expectation value of r squared, that depends on 1 over delta t. So if you do a simulation and you decrease this delta t, so the time steps get smaller and smaller, then the random forces get larger and larger. In fact, they scale with the square root of 1 over delta t. So r squared is proportional to 1 over delta t. That cancels one of the powers here. So this term is of order delta t. This term is omitted indeed because it's of order delta t squared. So this everything here is correct up to order delta t squared. What I arrive at is then the so-called Fokker Planck equation, and the Fokker Planck equation is it looks a little bit like a diffusion equation, but it has also a drift term, and it's a general equation for the probability density of stochastic variables that can be described by a Langevin equation. And so the Langevin equation gives you an explicit differential equation for the degree of freedom, which is v here, but it contains this random force r. And if you average, you get the distribution of all the v's at every time, and that's governed by this equation, the distribution. It's the solution to this equation. We can find the stationary solution, which we will arrive at if we wait long enough. Then the dp dt does not depend on the time anymore. So we put that equal to 0. And in that case, we find that the p, which is now only a function of v, so let me put that here. It's a function of v only. And it turns out to be a constant times e to the power minus mv squared over 2kbt. So you can see that if I put this left-hand side equal to 0, then I can drop out the gammas. So the gamma, the friction coefficient, does no longer occur in the equation. The solution just depends on kbt, and I find that this is the Maxwell distribution, the Maxwell-Boltzmann distribution. And in fact, this is the Maxwell distribution for a system where the average velocity is 0. Of course, you can also write the solution in this form, mv minus v0 squared over 2kbt. We have been dealing with particle moving under the influence of other particles, and so the motion of the particle under consideration can be characterized as a random walk. And for random walks, there is a very famous result which tells us that the displacement squared after long times is equal to 2d times t, where d is a constant. It's called the diffusion constant. So from the Langevin equation that we have analyzed, could we infer that indeed this is the behavior? That's question number 1. And the second question obviously is, what would be this d, this diffusion constant? So we try to find x squared t, but so far we have been dealing only with the velocity. Now there is a simple relation between the x and the velocity, just the time integral over v. And we can use the known solution for v from the Langevin equation in order to make some statements about the x. Recall that the solution for the velocity that we have found above for the Langevin equation had this form. First we have a homogeneous solution, and then we have to add a particular solution which depends on this random force r. So what we could do is take this v, plug it in there, and then calculate x squared, and then take the expectation value. That's quite a bit of work, and therefore we take a shortcut. This shortcut starts by writing up the equation of motion not in terms of v, but in terms of the x. So we get mx dot dot is minus gamma x dot, that's the drag, plus the random force. We multiply this equation on the left and right hand side by x, and then we will take the expectation value. But let's first do this, so we calculate x times x dot dot. And my claim is that we can write this as the time derivative of x times x dot minus x dot squared, because if I work out this, I get two terms. One is this term and the other one is that term. So in order to get that term, I need to subtract this velocity squared term. M times the velocity squared is twice the kinetic energy, can be related to kBt, equipartition theorem, and then we obtain the following equation. I've moved the term with the minus gamma to the left hand side and the kinetic energy to the right hand side, and replaced it by the constant kBt. And then here we have an RT times an XT. Then we take the expectation value everywhere, and recall that taking the expectation value means averaging over all the possible realizations of the random force. So here we have just an expectation value of x times x dot. Here we have the same expectation value. Here is a constant, so the expectation value has no effect. And here we have the expectation value of the random force times x. But the random force itself is completely independent of x, whether the particle is here or there. it will not have any effect on the random force, and therefore it's uncorrelated from x. So this, we can put the x outside of the expectation value, and then we find just the average value of the random force r, and we have already seen several times that that is equal to 0, so this term disappears from the equation. And so we have now an equation in terms of the expectation value of x times x dot, which we can call, for example, y. The solution can easily be found. It's a straightforward differential equation, and it reads c plus a times e to the power minus gamma t over m, where c and a are constants. C is not an arbitrary constant, but if I plug the solution into the equation, I see that it must be equal to kbt over gamma, and therefore if we take the time to infinity, then I'm left with just c, and that's kbt over gamma for this quantity here. If the time is taken at 0, then obviously this quantity should be 0, because x is the displacement from 0, from its position at 0. And from that I find that also the a is minus kbt over gamma. And it's important to note that we can write x dot as half times the time derivative of x squared. This implies that we need to integrate once more in order to find x squared itself. This is the derivative of x squared. And if we then perform the integral, we arrive at the following expression: 2 kbt over gamma times t plus 2 kbt over gamma m over gamma e to the power minus gamma t over m minus 1. Let us first find the short time behavior for x squared. So we are looking at short times, which means that we can Taylor expand this exponential here, and I've Taylor expanded here to second order. And it turns out that the term with t here is cancelled by the first order term here. The 0th order term is cancelled by the minus 1. And so I'm left with a term that scales with t squared. And this indicates that for very short time scales, and that short means that t is a lot smaller than m over gamma, we have ballistic motion, because the displacement itself is proportional to t, so the displacement squared is proportional to t squared. And that's just the motion of a free particle. And that tells us that the collisions have not yet shown their effect if the t is smaller than m over gamma. When the collisions come into effect, then we cross over to a different behavior. For large times, we can calculate the x squared too, and in that case let us go back to the original equation. Then the exponential will decay, and so we are left with this term and a term with a 1, but when t is large, this term will be much larger than that term, so we can safely neglect the minus 1. And what we then find is that we have 2 kt over gamma times t. And so that's 2 times the diffusion coefficients times t. And so what we find is that d is kbt over gamma. We have to express the diffusion constant in terms of the temperature and the friction coefficient, the drag. This gamma, there is a hydrodynamic equation for that. It's given as 6 times pi times eta times a, where eta is the hydrodynamic viscosity and a is the particle radius. So that's the radius of a particle. So if we have a large particle moving in a fluid and the particle has radius a, then it will experience a drag, which is given by this formula. This result is known as Stokes' law. When we were analyzing the Langevin equation for V, we also were interested in finding the probability distribution for V as a function of t. Now we have moved to the analysis of x, so it's natural to look at a probability distribution for finding a particle at position x, and that means that obviously pxt times dx is the probability to find a particle inside the small interval dx running from x to x plus dx at time t, so it's a time-dependent probability. Now we can make the following statement. V, as we have seen, is linear in R. Now x is the integral of v, so x is linear in v, and therefore x is also linear in R. Now RT has a Gaussian distribution, and because x is linear in R, xt is also a Gaussian distribution, because if we have a Gaussian distribution, consider for example e to the power minus alpha x squared, then if I change x by ax plus b, that will be also a Gaussian distribution. Any linear transformation leaves the Gaussian character of the distribution invariant. Now we have calculated before that the width of this Gaussian was 2 times d times t. That was the diffusion law. So the probability to make a step dx squared scales linearly with the time t, 2 dt. And therefore the transition probability, I call that t, and so it's a probability to make a step of size delta x within a time interval t, so I call this the transition probability. That should therefore be a Gaussian, because we know that the average of a step, of a random step, is 0. It should be a Gaussian, and the width of the Gaussian is known, so we can immediately write it up. And so we see that it also contains a normalization factor. This is just a normalization factor, which is induced by this term in the denominator of the exponent. Now, having this transition probability, we can write up an equation which gives us the evolution of this probability distribution P. So we start from a distribution at time t, and we want to make a statement about the distribution at t plus delta t. So if at a later time t plus delta t we are at position x, then at the previous time t we were at a position x minus delta x, and the probability to go from this situation to that situation is given by the probability to make a step of size delta x, and that's this t that we have just found here, the Gaussian probability distribution. And because the delta x is supposed to be small, if the time here delta t is also small, it's natural to make a Taylor expansion, and we can do that straightforwardly. So here we take first the delta x 0, so we get the p at x at t. So this is the situation where the particle does not move at all, because it was at x at time t, and it's at x also at t plus delta t. Then we have the first order term, where we have a first derivative of the p and a second order term with a factor of 1/2. And here is the t. I've left out the t dependence from the capital T. And if we then calculate the integral, we see that if I multiply delta x, here is no delta x dependence, but if we multiply that by the symmetric Gaussian distribution t, and we integrate over x, then due to the antisymmetry of the integral, this term will give 0. And so in the end, I'm left with this, where the delta x squared is the second moment of this distribution, and we know what that is. We can infer that directly from the Gaussian distribution. That distribution had a width of 2 times d times delta t, and because of the factor of 1/2, we find now this equation. Then we have here, if we move this one to the left-hand side, we see that it can be written as the first order time derivative times delta t, and then we obtain the following equation. We have dp dt, partial derivative with respect to t, is d times d squared p dx squared. And it's important to note here that this equation, it's called a diffusion equation, but it's only valid if the d is constant. So the d does not depend on x. So d constant. It's also possible to derive an equation for a non-constant d. In that case, there is also a x dependence in the t, so that has to be taken into account when Taylor expanding the terms here in the integral. And in that case, what you find is d dx, and then we have a x-dependent diffusion constant dp dx, where the p depends on x and t. So that's general. It's important to emphasize the assumptions that we have made so far. First of all, we have assumed that we are in the diffusive limit, and that is justified provided that the time step is larger than m over gamma, because otherwise we are in the ballistic regime still. On the other hand, we have made a Taylor expansion, and that is justified only when the delta x is small, so the transition step should be small. Well, looking at the distribution, it means that this delta x is a lot smaller than dt. Delta x squared should be a lot smaller than dt, and that is justified if the time is long enough. Now we move to an alternative derivation of the diffusion equation, which is via Fick's law. And Fick's law tells us that the flux of particles through some area, surface area, is equal to rho, that's the density of the particles, times their velocity. So I have here a small surface area A, and the flux is just the number of particles passing through A, and I calculate that I divide it by A, so I calculate it per unit area, and I calculate it per delta t, so these are the number of particles passing through A in time delta t. Of course, if I wait twice as long, I will have twice as many particles, so dividing by delta t makes it independent of this delta t, and the same holds for the area. If I double the area, I have twice as many particles passing through it. And Fick's law tells us that the flux through this area is given as the density of the particles, just the number of particles per volume, times their velocity, times their average velocity. And I will now derive that law in some detail. I consider the diffusion of particles along a one-dimensional axis, that's the x-axis, and we have a point x is 0, and we look at the flux. We want to calculate the flux through this point x is 0, and therefore we consider particles which at some time started off at a position x0, which is smaller than 0, and these particles are traveling during some time delta t, and initially they were definitely located at this position, but they will form a Gaussian distribution after some time, and so therefore we will have this Gaussian distribution expressing the distribution of the particles after some time delta t, which is obviously positive. And if you want to calculate the flux through x is 0, that's just the number of particles which have passed the point x is 0, and they are the particles which are on the right tail of the Gaussian. And therefore we can write up immediately an expression for the flux through x is 0 due to the particles coming from x is 0. Here is that expression. We have a Gaussian distribution, and I integrate only the part for the positive x's, and the x0, which occurs here as the center of the Gaussian, should be negative. So we have an x0 smaller than 0. And I can do the same for particles released at the positive x-axis. The blue Gaussian curve is centered at an x0 which is positive, and the particles which have contributed to the flux through the point x0 are the ones that I find in the left tail of the Gaussian distribution. And therefore the mathematical expression for this is the following. So we have for particles coming from the right the integral which is given here. It's the green shaded part in this picture. And now in order to derive the diffusion equation, we assume that at some time we had a distribution of particles which is given by rho of x. Each of those particles can diffuse according to these evolutions, and therefore we multiply this by rho at x0 and we integrate over rho x0, and that's the flux of particles passing to the right of x0. We do the same for this one. We multiply it by rho of x0 and then we integrate over all the x0s, and that is the contribution to the flux to the left. The flux to the right has a positive sign, the flux to the left has a negative sign, so we need to subtract this integral then from that integral, and this results in the following. We take the first expression, x0 being negative, and we integrate over all the possible positions. Here we multiply that by the density of particles at that position at time t, and then we wait for some time delta t, and then these particles are distributed according to the black curve, and this integral then calculates the red area for each of the particles starting off from the left. And then here we have the same expression, but then for x0 positive, and it has a minus sign because we are calculating now flux for particles going to the left. The rightmost integral can be reworked because we can swap the two boundaries of the integral. We can also change their sign, then nothing changes in the overall sign, so I still have a minus, and I have now an integral from minus infinity to 0 over dx0 and the integral over dx. I do the same for that one. I have a 0 to infinity. Nothing changes here because both x and x0 have changed sign, but there is a difference in the rho, which is here, here it depends on x0, and because I've swapped the sign of the integration variable, this is now rho of minus x0t. Also, since we shall be interested in short times, we expect the particles contributing to the flux to be located very close to x0. It is natural to make a Taylor expansion for rho as a function of x0. So we write that rho x0t is rho of 0t plus x0 times rho primed, and with rho primed I mean the derivative with respect to the first argument, so with respect to the x. And this assumption then simplifies this long expression here. First of all, we see that if I take rho 0t, and that term is the same for this one and that one, and then we see that the two integrals are completely identical except that they have a different sign, so they cancel. And so we should have a look at this one, because here we have a term with a plus sign here and a minus sign there. And therefore the result is the following. Here is the resulting expression, which has a factor of 2 because I have the same contribution for the first term as I have for the second term, however with a different sign, because the x0 has turned into a minus x0 there. And together with this minus sign I have a factor of 2. Then I can extract this term rho primed 0t in front of the integrals, and I have here an x0 which is negative. The integrand apart from that is positive, and so therefore I have a negative result. I have in fact minus rho primed 0t times the diffusion constant times delta t. Performing the integral is a little bit tricky, but it is in fact straightforward. So this is the result, and this is Fick's law of diffusion, or this expresses Fick's law of diffusion. What we have calculated is the amount of particles which during a period delta t flow through x is 0. And it was the net flow of particles, because we took the particles moving to the right with a plus sign and those moving to the left with a minus sign. So by definition, this is also j times delta t, and j is then calculated at x is 0. So it's the flux that we have calculated at x is 0. But of course there is nothing special about the point that we have taken. We have now taken the point x is 0. We could have taken any point, and therefore we have in general that the flux j as a function of x and t is d times, with a minus sign, the derivative of rho with respect to x at x and t. This is the one-dimensional version. It can be generalized to more dimensions, and then it reads jr of t is minus d times the gradient of rho r of t. And this is the famous Fick's law of diffusion. And what it tells us is the following. If you have a variation in the concentration of particles, the flux is always such that it tries to even out the distribution of the particles. So it always tries to flatten the particle density. Fick's first law, which gives us the diffusive current, is not yet the diffusion equation. In order to derive the diffusion equation, we need to combine this with a different law, which tells us something about the conservation of particles. So we consider a volume of V, which is bounded by a surface A, and we consider this change in the amount of particles inside V. So how does that change in the course of time? Well, the total amount of particles is the integral of the particle density over the volume, and if we compare that for t and t plus delta t, we have this expression. So this expresses the change in the amount of particles inside V. If we realize how the number of particles can change, we conclude that this can only change by particles passing through the surface area A, and the flux of those particles is j, so we have to integrate that over the surface area, and that is per unit time. So if we have a delta t here, we need to multiply this by delta t. What is important in writing up the right hand side is that we neglect the effects where a particle, or the processes in which a particle could just disappear into a sink, or it could just appear from a source. So there are no sources or sinks. So only particles moving through the surface can change the total number of particles inside the volume. We then note that the left-hand side can be written as the derivative of rho with respect to t times delta t. That delta t cancels against this delta t, so we have then that the derivative of rho with respect to dt is equal to minus j dot dA. And for that last expression, we use the divergence theorem in order to convert the surface integral into a volume integral at the price of putting a divergence in front of the j. And if this should hold for any possible volume, so this should hold for any volume that we can think of, then we obviously have that d rho dt is minus a divergence of j. So we have d rho dt is minus divergence of j, and that expresses in fact the conservation of matter, and it's called the continuity equation. Combining the continuity equation with Fick's first law So we use that J diffusion is minus D times gradient of rho. We plug that in. We immediately obtain the diffusion equation. And we have arrived at a similar equation before, but that was in terms of P, the probability to find a particle at a certain position. And obviously these two are strongly related. Rho is proportional to P. And so you see that if you plug in P, the probability to find a particle somewhere, then that also satisfies the diffusion equation, which we have now derived in two ways. The way that we have just seen was using Fick's law that we derived first in quite some detail. We combined it with the continuity equation, and before we had used a different approach, and that was for the probability. And that was from a time evolution of the probability, but in both cases the assumption that was the fact that the x satisfies a Gaussian distribution probability if we release a particle from a particular position for some time. So far we have considered diffusion in the absence of a systematic force. So the Langevin equation contained just the drag and the random force. Now we introduce the systematic force once again, and for a physical picture you could think of gravity. Particles are dragged towards the bottom of the system, or you could think of an electric field which pushes particles that have a charge in one direction. And in order to make progress, we will now assume, for simplicity, that this force F is constant in time and does not depend on the position. If we assume F to be constant, we can consider the situation in which the velocity is stationary. In that case, the time derivative of the average velocity should be 0, and from the right hand side we see then that minus gamma v plus f should be 0. If the force is absent, the average velocity is 0, but if the force is there and it's constant, then we will find a constant velocity and therefore a constant flux which is induced by this drift force. So that's the drift flux, Jf. And what happens if the system is closed is that if the particles move towards one direction, they will heap up at one side of the system. So for example, if I have a container and I drive all the particles to the right, then they will heap up towards the right wall. And so because there is now a strong slope in the density of the particles, there will be a flux which counteracts the drift force. So, and that's the diffusion flux. So if in the end we will reach a situation in which the drift flux is balanced by the diffusive flux, and then obviously the particles don't move anymore. And if we have that balance, we have the following equation. The gradient of rho divided by rho is F over gamma d. And so we generalize this result now to forces that really depend on the position, because then you can maintain the same argument in the end. If the force does not depend on time, but it depends on position, this flux will depend on position, but in the end you will have a diffusive flux, which is also depending on position. And we will have this balance equation which leads to this final result. Now it's useful to write this force as the gradient of a potential. So here we see gradient potential divided by gamma d, and we can rewrite the left hand side as the gradient of the logarithm of rho, and that enables us to write up the solution right away. The solution is then given directly as a constant times e to the power minus u over gamma d, and that is the distribution that we find in equilibrium. But on the other hand, we know that in equilibrium this should be the Boltzmann distribution, so it should be a constant times e to the power minus u over kt. and therefore we see that gamma times d is kBt. That is the same result as we obtained already before, so the diffusion constant together with the drag can be related to kT. In the absence of a drift force, we had a diffusion equation which described the probability to find a particle in a certain position. And it's interesting to ask ourselves how we can generalize that diffusion equation to the case in which there are also drift forces present. We perform the calculation along the same lines as before. So we take a distribution p at time t. The particle is then at position x primed, which is delta x away from the final position x, and t is the probability to move over a distance delta x, but it depends now on the starting position, and the delta t is the time that elapses. We calculate the moment delta x for this distribution, this transition distribution t, and later we shall also address the delta x squared. Now the delta x is caused by diffusion and by drift. The diffusion contribution averages out because the diffusion doesn't have a preferred direction, so the linear term in x doesn't have any contribution, and the force gives an average velocity of f over gamma as we have just seen, and we multiply that by delta t in order to find the displacement. So that's the first moment of the transition probability. It's the average displacement of the particle during a time delta t. We also calculate the second moment to the lowest order in delta t, and the diffusive part gives us 2d times delta t. There is obviously also a ballistic part, but that ballistic part scales with delta t squared, so that's omitted here. So the second moment of this distribution to first order in delta t can be written as 2 times d times delta t. Now we return to this evolution equation and we multiply the left and the right hand side by a delta function x minus x0, and then we integrate over x. So not over the delta x, it's the integration which is here, but over the x, that's this x. We then obtain the following result. So in the left hand side, if I multiply by this delta function and then integrate, I just replace the argument x here by an x0. On the right hand side, I do that not immediately. I just write the p here and the t, just like they were here, except that I have replaced the x primed here, that's the previous x, by x minus delta x. That's the same, but I would like to have only x and delta x as variables and not a third variable x primed into the problem. And then I have here my delta function and I integrate over x. It is then natural to Taylor expand that equation, and if we take the zeroth order term on the right hand side together with the delta function, it gives me a minus px0 comma t on the left hand side. So just as before, we can write that as delta t times dp dt. And here I have restricted myself to the first order terms. The second order term, I will analyze that later. It would be too complicated to take it into account right away. So I put a 1 here in order to emphasize that on the right hand side we only take the first order Taylor expansion in delta x. So we have a p here at x minus delta x, so that gives me a first order Taylor term minus delta x times dp dx, and the same for t. The second term here gives me a minus delta x coming from this argument dt dx. And so the dp dx is okay, the dt dx is a little bit inconvenient, but we can do something about that. In fact, we had seen before that the first moment can be written as the force divided by gamma of this. And if I take the derivative with respect to x on the left and on the right hand side, then we obtain the following equation. I have d dx of the first moment, so that's this. Then I have df dx divided by gamma multiplied by delta t, and then on the right hand side I have d dx of t, because this x primed can be written as x minus delta x. So I take here the first derivative, and now, lo and behold, this term here is exactly the same as the one I have in this integral, and the rest does not depend on delta x. So I can just replace the integral over delta x by df dx over gamma times delta t. And that yields the following result. I have two integrals, one with a derivative of p multiplied by f, and one with p multiplied by the derivative of f. Well, putting in the delta functions then gives me immediately the result. And that result is minus 1 over gamma times the derivative with respect to the x0 of the product of p and f. So that is the result of the first order Taylor expanded terms in x. However, the second order terms also give a contribution, so I should consider those as well. These terms are analyzed exactly in the same way as above, and so we have again the same result. It's just the diffusive term from the diffusion equation, which is just unchanged in this case. So I should add this term here, and then I end up with the final equation. The Shmolukowski equation, which is more or less like the diffusion equation. The term on the left hand side together with the second term on the right hand side, they give me the diffusion equation, and we see that the drift force F has introduced an extra term minus d dx, p times f over gamma. And obviously this equation, well, we have assumed the f is constant. If f is constant enough over a certain area where the other quantities have a rapid variation, then this equation is still invariably valid. So the Shmolukowski equation can be used for any kind of transport process where we have drift in addition to diffusion. As usual, the probability to find a particle somewhere is proportional to the density, so we can also read rho instead of the p, and then the Shmolukowski equation in more dimensions can be rewritten in this form. And if the time is again taking very large, then we should have that the distribution does no longer change in time, so that's the equilibrium situation. And then we have equals 0 on the right hand side, so now we have an equation that we can solve, and again we find that rho is equal to e to the power minus ur is over gamma d, hence we have that kbt over gamma is d, and that's the Einstein relation. And this is in fact very close to the derivation that we have given above, but although there we just use the properties of v. So here we had the same equation, the Boltzmann factor, and from that we inferred again this Einstein relation. And it's a relation between the drag and the diffusion coefficient on one hand and the temperature on the other hand. It is interesting to apply the Shmolukowski equation to the transport of electrons that are moving in an electric field, for example, inside a conductor. Then the electronic current is given by rho, which is now not the number density, but it's the charge density, so it's E times n, where n is the number density. So it's minus rho times f over gamma. F over gamma was the velocity, as we have seen before, and if you multiply the charge density by the velocity, we get the electric current. That's equal to minus E times the diffusion current. So normally the diffusion current is a number current, and because I want to relate it to the electric current, I have this extra factor of E. But the rho then occurring here is the electric charge density, so I have a minus d times d rho dx. And I know for a fact that the rho has the form of constant times e to the power minus e v of x over kbt. We have seen that several times before. Taking the derivative is straightforward, and I get the gradient of v, the gradient of ev. And the gradient of v is equal to the force, the electric force, and that's E times the field. And so we have E times D times the electric field over kBt times e to the power minus EVx over kt. And now I use the fact that I can replace this c times the exponent by rho. That was rho. So I simply write it now in this form. J is proportional to rho. That's identical to this equation. But now we have a more specific prefactor here. In electricity, we usually relate the electric current to the field using a quantity sigma, which is the conductivity. So in particular, the electric current density is proportional to the field with a proportionality constant of sigma.